All right, welcome to the final review. We made it. So my plan is this is the last lecture this week. There will be one more final review lecture next week, and then we're supposed to have one more day of class next week. You can just use that to watch the final review again. How about that? So that is my gift to you, a day to study. So let's get started on the final review. I just have a bunch of topics. I can't, of course, teach you the whole class all over again, but here are a list of topics and some examples. That is hopefully going to give you the best bang for your buck. So yeah, let's talk about induction and recursion. This all started due to sequences. You can have arithmetic sequences, geometric sequences. Here's an example arithmetic sequence. Like you have start with 4, then it's 8, then 12, then 16, then 20. That's an arithmetic sequence because there's a common difference each time. We're always adding 4 plus 4 plus 4 to get to the next one, plus 4 to get to the next one, etc., etc. It's always plus 4, plus 4. And sequences are referenced using indices. Like this is sequence number 0 if the sequence is called S. This is S of 0, S of 1, S of 2, S of 3. Like you could have started it totally at like S of 1 if you wanted to. Not a big deal. So that's how you can define an arithmetic sequence. You can make a geometric sequence as well. Instead of a common difference, there's a common factor involved. So 1, 2, 4, 8, 16, 32, that's just all the powers of 2. And the way that you get at the next value in the sequence is you just keep multiplying the previous one by 2. And that is your, that's the way you do it. Once you have a sequence, you can always classify it into decreasing, non-increasing, non-decreasing, and increasing. So give you some ideas of that. So decreasing sequence is one like this, 5, 4, 3, 2, 1. It's always getting smaller. A non-increasing sequence is either always getting smaller or staying the same. So it's like 5, 5, 4, 4, 3, 2, 1. That's totally fine. A non-decreasing list is one that's always staying the same or getting bigger. So it could stay the same, but if it ever gets to be different, it's got to be bigger. 3, 4, 5. And then finally, increasing is always the next element is bigger than the previous element. It doesn't have to be in order like this. It could have gone like 1, 8, 17, blah, blah, blah. It just always has to get bigger. So those are some sequences. You can define sequences with equations, of course. Like let's define the sequence A to be that every element of the A sequence is, element n of the A sequence is n squared minus 4n, and it starts at 1. So like, what is A of 1? What is A of 2? What is A of 3? We can generate this sequence. A of 4, A of 5, A of 6. And it goes on forever, of course. It's an infinite sequence, this one. But how does it work? It's, all right, you just take this 1. It's like 1 squared minus 4 times 1, so that's negative 3. And then what's this one? This is going to be, now it's 2. It's 2 squared minus 4 times 2, so it's 4 minus 8, so negative 4. 3, 9 minus 12, so negative 3 again. Interesting. Then we have 4. 4 squared minus 4 times 4, that's 16 minus 16, that's 0. And then we have 25 minus 20, that's 5. 36 minus 24 is 12. And so it keeps going after that as well. So that's our sequence. It is, you can see that it's sometimes increasing, sometimes decreasing, so it's none of these. It's just its own weird thing. So that is a sequence that you can define like that, and hopefully that helps. A lot of sequences can be defined using a recurrence relation, and a good example of that is like the Fibonacci sequence. So you define the Fibonacci sequence with a recurrence like this. Like you define the 0th Fibonacci number to be 0, the first Fibonacci number to be 1, and then from then on, for every f where f of n where n is greater than or equal to 2, your f of n is equal to f of n minus 1 plus f of n minus 2. Just go over those two previous ones, and that will generate a sequence for you. And it works like that. And then here's an example of using a sequence. So like here's an example where example sequence called C. C1 is 4, C2 is 5, and then everybody else is the product of the previous two. So it's very similar to Fibonacci. It's just products instead of plus this time. So C1 and C2 are given. That's 4 and 5. And then C3 is going to be C2 times C1 according to this definition. So that's 20. C4 is 20 times 5. That's 100. C5 is 100 times 20, that's 2,000. C6 is 2,000 times 100, so that's 2,000 with 2 more zeros. 200,000. And it goes on and on. But that's a recurrence relationship. You're gonna say how this sequence is defined in terms of previous elements. It's kind of recursive, and so you see the recur part again. What about summations? I just have a bunch of things to say, so let's just keep going through them all. A summation looks like this. It's just this big capital Greek sigma, which is supposed to stand for sum all these things from this starting point to this ending point, and you calculate each term to sum together with the thing that you put over here. So here's a silly example, like Jeff Bezos, for example, makes a ridiculous amount of money per second. It's probably more now, but let's use a summation to represent the quantity that he makes in a day. So we can use a summation to talk about that idea. So it's like, all right, how many seconds are there in a day? Because this is per second. Well, start I at 1, go to I being 60 times 24. That's how many seconds are in a day. And every time, every I, add a new $3,715. So each I, add this up. And so that's a summation that represents how much Jeff Bezos makes in a day, for example. Here's another example. Let's do the sum of the first n elements that look like this. 2 times 13 plus 3 times 23 plus 4 times 33, all the way n of those in that pattern. So the next one would have been 5 times 43, then it's like 6 times 53. See that? Dot, dot, dot. And so we want to do n things. We'll use an I variable, why not? It'll start at 1, go to n. And then when we're here, for example, let's say that this is like I equals 1, this is when 2, 3, 4, this would be when I is equal to 5. Do you see the pattern? Using I, what do we have to sum each time we have a new value of it? It's always going to be, well, if this is I equals 5, this is going to be I equals, well, I plus 1, that makes the 6. Always makes the 6. I plus 1 makes the 2 as well. Then it's always, like if it's 1, it's 13. If it's 5, it's 53. It's going to always be I times 10 plus 3. I times 10 plus 3. Because that'll generate the 53 when we're here. When I is 5, and then when I is 1, it'll generate the 13. That looks to be the proper way to do it. So that's how you could represent this summation once you notice the pattern. And of course, there are closed forms that you can go back and study and all that. But that gives us some sequences, some things that we care about, and this led to induction. So induction was when you proved something for every natural number, for example. You had some predicate that you wanted to say it's true for this one, it's true for this one, it's true for p of 2, it's true for every p. You're usually proving something in the form like for all natural numbers, p of n is true, which is pretty cool. And it's a very recursive kind of thing. You got a base case and you got an inductive step, which gives you access to this inductive hypothesis. It's all very nice. So the base case was when you're saying, like, I know p of 0, it's true. And the inductive step was saying, all right, for every k, if you give me a proof of p of k, I can modify that. I can transform it and give you back a proof of p of k plus 1. So that's pretty nice. So that's those are the two pieces together, and taken together, they let you prove everything. And as you're proving this is just a direct proof. You get to assume this, prove that. This assumption, right, is your inductive hypothesis. That's your p of k. You get to use that as firepower to prove p of k plus 1, right? So just as a quick example, let's do the classic closed form. The sum of all the numbers from 1 to n is equal to this, n plus 1 times n over 2. And we can prove that with induction. So proof. The base case is like when it's 1. Let's prove that all the numbers summed from 1 to 1 is equal to this fancy thing. Base case. P of 1, that's the smallest thing we could possibly show here. So P of 1, we have to show that the sum of all the numbers, right, I equals 1 to 1, of I is just equal to 1. All right? And we have to show that to be the closed form as well. So it's like, that's equal to, it's equal to, well, which we know is 1, first of all. That's got to be equal to n plus 1, so 1 plus 1, 2 times 1 over 2, which is equal to 1. And so it all checks out, okay? I hope that makes sense. So that's the base case. And then the inductive step, let's do that on a different slide. Inductive step. is you get to assume P of k, assume P of k is true, and use that to prove that P of k plus 1 is true. So assume P of k, which is apparently that the sum of all the numbers from 1 to k is equal to k plus 1 times k over 2. That's how you can extract that, k plus 1 times k over 2. And then we're going to use that, what we need to show now, to show pk plus 1. And that is that 1 plus 2 plus all the way to k plus 1, there's a k in there though, k to k plus 1, is equal to the same idea, just replace this with k plus 1. So it's k plus 1 times k plus 1. The k plus 1 plus 1 is k plus 2 times k plus 1, again over 2. So that's what we're trying to show. And we can use P of k if we can find this summation somewhere. And what do you know? It's part of the sum of all the numbers from 1 to k plus 1. I can see the sum of all the numbers from 1 to k. All right, so let's break it up. Let's be like, all right, 1 plus, we need to show that this is equal to that. So the left side, 1 plus 2 plus all the way to k plus k plus 1. That's equal to, rewriting using the inductive hypothesis, that's equal to, well, I know that from 1 to k it's equal to this. I'm assuming that. That's equal to k plus 1 times k over 2. And I still have this k plus 1 that I didn't extract anything from. So that's plus k plus 1. And I need to get that looking like this. So let's make some common denominators. This is k plus 1 times k over 2 plus 2 times k plus 1 over 2. And all right, that's equal to, now let's do that down here maybe. That's equal to, let's just multiply. This is k squared plus k. Oh no, my PowerPoint is unhappy. That's k squared plus k. And this is 2k plus 2 over 2, which is equal to k squared plus 3k plus 2 over 2. And you can factor this, believe it or not, that really ends up being k plus 2 times k plus 1 over 2, which is, that's the left side, that's the right side that I needed to show. And so that proves the inductive step, which proves the whole thing. Taken together, you give me a number from 1 onwards, I can show you that P of k is true for every k. P of n is true for every n. Starting at 1, let's say. So that's induction in a nutshell. Hopefully it's ringing a bell. Let's see what else we got. Recursive set definitions. So this is all very similar together. This is induction and recursion stuff. You can define a set recursively in terms of some base elements and then some rules to build up from those. So here's an example that is kind of like what you did in your homework. So here's a recursive definition for a set S. So we're making a set S, some wobbly thing, and we're defining it over this alphabet AB. And so those are the only characters that can appear, including the empty string though, as we're building our stuff up. So the base case is that we say that the empty string and B is an S. So empty string and B, that's in our set S that we're building. And then our recursive rule is that if you can find something in something in S, call it S, take it out, these other things are also things that should be in S. That's how you build it up from smaller stuff. And let's list the strings of at most 3 in S. It can be bigger though. So let's see here. What are the rules? So like lambda is an S. The empty string is an S. And all right, that could be an X. That could be our X. So lambda A then. Lambda A is an S. Lambda A is an S. And then lambda AB is also an S. We're going to add those then. And remember, lambda is the empty string. It just goes away. So that's just A and AB. So here is A and AB. And then like B. B is also an S. So B could be X here. And that means that BA is in here. And that means that BAB is in here. You see that? That's quite nice. Now we have A that's in here. We could let A be X. Now we have AA. Better be an S. AAB. Better be there. Let's see. What else? AB is in there. Let's do, all right, that means ABA, because X could be AB. So ABA could be in there. ABA, ABAB is in there. And then what else we have? I think I did all these as rules. Let's do AA and then BA, and then we'll stop. So BA could be in there. So BA could be X. So it's BAA is in there, and so is BAAB. And then finally AA is an S. This is an infinite set, by the way. I'm just going to do at most 3. We have, well, AAA. And then, because AA is going to be that's our X, then it's AAAB is also in there. And I think that's all of them. I can't remember. So the strings of at most 3, I'll underline those in green. But there are more strings, of course. You can like take the AAA and have that be X and make AAA and all that fun stuff. But the strings of at most 3 are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of them? Let's make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's as many as I wrote in the last one. I don't think there's any duplicates either, but I could be wrong. But I think you get the idea now. So that's how you can use, and I'm underlining those ones of at least 3, at most 3 in green. That is how you can use a recursive definition to build up an infinite set. Of course, remember, there are more things here. ... Maybe I'll use blue dots. It's an infinite set. You can have infinitely sized strings in it, but at most 3. Those are all the ones, I think. Because every time you pick something out, you're going to put in another thing of the next bigger one. And so I could stop now, and that's at most 3. So that's recursive set definitions. Of course, we've learned well before this class about recursive algorithms. So let me just walk you through that. You can then go and prove that a recursive algorithm is correct using induction, and I'll do that too. So here's an example. Let's do factorial. So you break the factorial up into a base case and a recursive case. You notice that, like, all right, here's the smallest factorial I care about, 0 factorial. Define that to be 1. And then for an arbitrary factorial, what's your recursive case? N factorial, that's equal to n times n minus 1 factorial. That's what you notice. And then you can implement that. You turn that into code like C++, int fact, int n, that's equal to, well, got to figure out if you're in the base case or the recursive case. If it's n is 0, return 1, else return n times n minus 1 factorial, but this is recursive, so calling ourselves should go off and produce that. So that's your implementation. Let's do all the cool stuff that we learned how to do. So let's find the recurrence relation, T of n, for the number of operations for an input of size n. All right, so let's think about this. T of n. Well, I think it's easiest to use like a little tree. So T of n, if I call factorial on n, what does it do? Well, assuming it's usually in the recursive case, it's like, it's got to do some constant work, multiply its n by some result. So that's like constant work at this level, but then it also sends off some work to the previous level. It calls off to n factorial of n minus 1, which is going to take t of n minus 1 time, whatever that is, which is going to be probably the recursive case again until it gets down to the base case. So that's going to take constant time to do the multiplication, but it'll also have to call off to t of n minus 2. You see how that's working? Which again needs to multiply its stuff, assuming it's in the base case, and then call factorial of n minus 3, which will take t of n minus 3 steps, operations. And so eventually it's going to get down to the base case, t of 1, and that will be constant time. You just return 1. So the question is, all right, I see a lot of constants. How many are there, though? How do we add this all up? I guess the main question is, what is the height of this recursion tree that we're drawing here for ourselves? How tall is this? Well, this is the call to factorial of n. This is the call to factorial of n minus 1, n minus 2, n minus 3, all the way to 1. There's n of those. This is n high, and there's constant work at each level. You see that? That's going to be your analysis. At every level, t of n, it's going to be we're going to call the smaller factorial, which is going to take t of n minus 1 time. That's the recursive call. And we're going to add that work to, well, we're going to take that answer once we get it back from the recursive call, multiply it by Rn, and return that. That's all constant work after that. So plus theta of 1, let's say. Theta of 1 work. That's like the multiplication, the returning. That's the rest of the work at each level. Let's see here. Can we solve it using the master theorem? Does it look like this? Does it look like a times t of n over b? No, it's n minus 1, sadly. So no, can't use the master theorem. Sad day, but we can do it ourselves. We can use this tree, and it's like, all right, it's n levels, constant work at each level. So it's n times constant, which is going to be theta of n. That's going to be our analysis. All right, and now we took so much time learning induction, we can prove that factorial is correct. We can prove that any recursive algorithm is correct using induction. The recursive call becomes a appeal to your inductive hypothesis. So here's my theorem. For all n greater than or equal to 0, of course, factorial of n, when you call it, the one that we just implemented, this guy, it will give back exactly n factorial as a result. All right, that's what I want. And here's my implementation of that if we need it. I don't know. Might as well save it on this slide just in case. So there it is, if we need it. And this is going to be, what are we trying to prove for all n? This, for every n. So this is our p of n right here. So we're trying to prove for all n, p of n. And sorry, n factorial. I'm not just saying exclamation point for fun. That's our p of n. The factorial of n is equal to n factorial. And that's what we have to prove for all n greater than or equal to 0. So you kind of prove it as you programmed it. You have this base case. That's going to be your base case for your recursion, or sorry, for your induction. The base case for the induction is we got to prove p of 0 is true. And what's that saying? It's trying to conclude that fact of 0 is 0 factorial. Whatever fact of 0 returns, that's equal to whatever 0 factorial is. And fact of 0 will return, just reading the code, it returns 1. 0 factorial is defined to be 1. So that checks out. That's the base case. And then the inductive step will be in charge of proving that the recursive case is true. It's always assume p of k, use that to prove p of k plus 1. So assume p of k is true, which is that fact of k is equal to k factorial. And use that to show, what we need to show now is that p of k plus 1 is true, that fact of k plus 1 is equal to k plus 1 factorial. All right? And if we can use that, we can find the factorial inside of it, it'll all work out. So the question is, what does fact k plus 1 do? It's going to return n times factorial of n minus 1, where n is k plus 1 right now. So it's going to return k plus 1 times the factorial of n minus 1, or sorry, k plus 1, so the factorial of k. Hoo-hoo, I have a inductive hypothesis dealing with factorial of k, so this gets translated into k plus 1 times factorial of k is assumed to be equal to, and give back k factorial. This is k factorial with another k plus 1 at the front. That is equal to k plus 1 factorial. You see that? That's what you should be thinking about as you're proving that, or as you're writing this code. That's what you think about. Like, assume that this gives me back the right thing. Multiplying it by this builds up the next answer correctly. That's what we just had to show. So, and this is of course equal to what I wanted it to be equal to, so that checks out. And so I have a base case and an inductive step. I have just proven for all n greater than or equal to 0, factorial of n gives back the right answer. Gives back the true mathematical factorial of that number. And that is how you can prove your recursive algorithms correct. It all gets broken down just like recursion. All right, so yeah, let's keep on trucking. I got some more slides about some other things, and we'll go from there. So let's talk about graphs. So there was sadly a lot of terminology that we had to learn with graphs. So let's talk about all that. Graph can be either directed or undirected. So here's like an example graph. And this one is directed. It has edges with arrows, like from here to here. Starting here, you can go in this direction. Starting here, you can go in this direction. You can go in this direction. You can go in this direction. That's a directed graph. And then here's an undirected graph. It's just like there is an edge. You could go here. You could go here, or vice versa, in any order, any direction. Does not matter. So that's an undirected graph. Let's see. Vertices are the dots. In my example, the edges are the little lines connecting them. The degree is usually mostly talked about in an undirected graph. It's just the number of edges along this thing. So it's degree 3, this degree 2, just number of neighbors that this edge has, this node has, vertex. Degree 3, degree 2. We can talk about the degree of the whole graph by adding them all up. You can pick out a part of a graph as a subgraph. So like a subgraph of this graph is just pick some vertices, like these 3 maybe, and pick some edges between only those vertices, like maybe these 2, and there's your subgraph. Let's see, you can have parallel edges, which is usually uncommon, but it's like there's 2 ways to get here: the toll road or the free road. You can have parallel edges in a, I guess, in an undirected graph as well. I'll draw that a little bit nicer though. Be like that or that. That's a parallel edge there. You can also have self loops. Usually it's more common in a directed graph, but you can totally have a self loop undirected. Looks like that. That's possible. All right, so that's all that. Let's see what else. The hardest terms to keep straight are walk, circuit, path, and cycle. If you study it hard enough, I promise it will make enough sense. But a walk is just very generic. It's telling you, like, I moved in this direction. I moved this way. I started at this vertex. I followed this edge. I'm at this vertex now. I followed this edge. I'm at this vertex now. I followed this edge. I'm at this vertex now. It tells you exactly what happened in as much detail as possible. It's a walk. A circuit is a special kind of walk. You can't visit edges more than once. Let's see here. So, like, let's use undirected graph stuff. Can't use more edges. No, any edge more than once, but you come back to where you started though. So a circuit requires you to come back where you started. It's a walk. Can't use edges more than once though. So it's like I can't go here and come back along that same edge. That is not a circuit. But this would be a circuit, for example. Let's see. A path is when you are going places and you cannot use an edge or a vertex more than once. So it's like this is a path, but trying to come back around, no longer a path. This is a path, but once I wrap around like this, I visited a vertex another time, no longer a path. Yeah. A cycle is a path, but the first and last vertices are allowed to meet. So like, this would not normally be a path, but it is a cycle. It's just a special path where you allow the first and last vertices to be the same. You cannot reuse the edges though, so like this is not a path or a cycle. So that's important. So like this is a little path. It's like that, and then a cycle would look something like, let's see, something like that. You come back around. It's a path, except for the first and last edges. The first and last vertices, they're allowed to be the same. Let's see here. So graphs can be connected. Let's see here. How do I want to say this? Graphs can be all connected like this. Let's take this to be one graph by itself. That is a connected graph. All the vertices are connected to each other. There's a way from everybody to everybody else. A graph that is disconnected looks like this. Like this, pretend that this is the whole graph. Like here's a piece of it. All these things are connected. Here's another piece of the same graph. You see how it's like isolated? Here's another piece of the graph. It's like take this as one big graph. It is disconnected. Do you see that? Kind of logical, I hope. So that's your graph G. It is disconnected, but even if your graph is disconnected, you can talk about the little connected pieces inside of it. Those are called connected components. Like here's a connected component. Everybody's able to get to everybody else within this component. And this is another connected component of G. This is another connected component of G. So you can always split up a disconnected graph even into connected components. If you just have one graph and the whole thing's connected, then it is just one big connected component, technically. Next we have regular graphs, cliques, or KN, and then KNM. So, all right, a regular graph. What is that? That's one where each vertex has the same degree, all same degree. So here's a regular graph. Every vertex has degree 2, 2, 2, 2. They all have 2 neighbors. And I'm sure you can come up with more. Cliques, or K sub n for a certain number of nodes n, look like this. This is K4, for example. It's technically also regular. It's just a special kind of regular graph. It's everybody knows about how to get to everybody else. So like here's K4. It's got 4 vertices. That's what the 4 means. And then every edge that could be there is there. It has a way to get to everybody else. So that one knows how to get there. Got 3 neighbors. This one knows how to get everywhere. This one knows how to get everywhere. So you have all these edges. Everybody can immediately get to everybody else. That is K4, for example. Try drawing K5 to prove that you got it. And then you have this weird looking thing, K some number comma some other number. And this is what it looks like. Here's like K34 as an example. This kind of graph, it is connected in a special way. It's like you have a set of 3 vertices and you have a set of 4 vertices, and there's like a partition between them. Everybody over here knows how to get to everybody to the right of it, but it cannot immediately get to any of its neighbors like that. So like node knows how to get to this guy, this guy, this guy, and this guy. They're all there. All those edges are there. This one knows how to get to everybody over on the right. 3, 4. This one also knows how to get to everybody up here. 1. Let's try and draw that a little bit better. 1, 2, 3, 4. And so you can automatically see that there's 3 times 4 edges in this graph. It's a special kind of graph where there's like a partition. All these guys are immediately able to get to everybody on the other side, but they're not immediately able to get to themselves. Like there's no arrow like that. That's what K34 is. So KNM in general, I think you can see how that generalizes. So that's that. What about storing graphs inside of a computer? So you can have representations of graphs. The 2 common ones are adjacency lists and adjacency matrices. So here's an example graph. Let's say that we have 4 vertices, and I will label them as A, B, C, and D. If only I could draw a B today. C and D. And let's say that we have these edges. It's an undirected graph. In an adjacency list, you have every vertex mapping to the list of all the things that it's connected to. So A would map to, what's it connected to? The B and the C along these 2 edges. So there's a list there. This would have a B and a C in it, this list. And then B is connected to A, C, and D. You'd store that like this. In some order, it doesn't have to be alphabetical order. C is connected to A and B. Could very well have been B and A, though. Order doesn't matter. And then D is only connected to B. So you just have a single element list over there. And so that's the adjacency list representation. It's very compact. It's only you only put stuff when there is an edge. Adjacency matrix, though, you kind of have to, like, it's either a 1 or a 0, and you have very many possibilities. So adjacency matrices deal with rows and columns like A, B, C, and D, A, B, C, and D, and talks about how they're all related to one another. So like you put a 1 or a 0 depending on if this is connected to this. Like in this slot, is A connected to A with an edge? No, there's no self loop. So you put a 0 here. There's no self loops anywhere. So you put a 0 when there isn't an edge. And you put a 1 when there is an edge. There's an edge from A to C. So from A to C, you put a 1. And it's undirected, so there's also an edge from C to A. So from C to A, you put a 1 here as well. And it might actually be easier to just like draw some slashes here. Whee. slightly better, I guess. Okay, what about the rest? So we have A and B. So from A to B and B to A, you got a 1. Undirected graphs are symmetric like that. Let's see here. What about from B to C? B to C is a 1. C to B is a 1. And then B to D. B to D, and D to B. And I think there's zeros everywhere else. There's nothing from A to D, nothing from C to D, nothing from D to A, nothing from C to D. So that would be our adjacency matrix. It takes up a bit more space because you have to say what's not there in addition to what is there. So it depends on what you're trying to do, which representation you'd prefer. But those are the two most common ones. And then finally we have our Euler and Hamiltonian stuff. We had Hamiltonian cycles and paths. That's a cycle or path. That includes every vertex in the graph. Doesn't have to include every edge though. So here's an example graph. Let's do K4. So like if this is your graph, a Hamiltonian cycle or Hamiltonian path, it's one that includes every vertex. So here's a Hamiltonian path, like from here to here, here to here, follow this edge, here to here. That would be a Hamiltonian path. You've now visited every vertex. To make it a Hamiltonian cycle, you just got to close it off. So there's the Hamiltonian cycle as well. So that's that one. An Euler circuit is one that includes every vertex and edge too. So let's see if I can discover this one again. So like if this is your graph, an Euler circuit would visit every single edge and vertex and not repeat anything. All right, let's moment of truth. Who knows if I can remember all this? Boop. I think I already messed up. So it's like one you have to like draw triangles, I think. Oh, yes, yes, yes. I'm never going to remember that, but that was it. Every vertex and edge only once. So that's Euler and Hamiltonian stuff. And then finally, graphs led into trees. What are trees but a special case of graphs? And so there are plenty of things to talk about there. There's a bunch of terminology. There are free trees versus rooted trees. Like a tree is just a graph, and with some special restrictions. Like here's a bunch of nodes connected to one another. No cycles. Looks like this. This is a free tree. If you don't specify like there's a root somewhere, like just no, everybody's the same. There is no top of this tree. That's called a free tree. But if you go and specify like, oh, there's the root, or maybe that one is the root, who cares? Then you have a rooted tree. And then you can talk about the levels of things and stuff like that. But yeah, free trees are just chilling by themselves. There is no root. It just looks like that or something. Who knows? Once you have rooted trees, you can talk about a lot of these terms. So here is an example rooted tree. This one has 3 children, let's say. This one has 2 children. And this one has just 1 child. So that's my tree, and the root is, of course, up top here. Root. And you can talk about levels. This is like level 0. It's the distance away from the root. This is level 0. This is level 1. This is level 2. This is level 3. 1, 2, 3. That's all there. You can talk about the height of the tree. That's the maximum level. So the height of the tree is 3. The parent-child relationship, like here's a node. Its parent is the root, and it has 2 children that have it as its parent. Ancestors, of course, make sense. Like everybody's an ancestor of the root. This node, or how about this node? This node down here has this as an ancestor, this is an ancestor, this is an ancestor. A parent is technically an ancestor too. It's who you came from. Leaves have no children. So like these are leaves, this is a leaf, this is a leaf. Everybody else is not a leaf. It's an internal node. And then you can talk about a subtree. It's like pick a new root, essentially, and then take everybody from then on. Like here's a subtree, for example. A leaf in a free tree is just a node has 1 outgoing edge, or just 1 neighbor. There is no concept of outgoing versus incoming. So this is a leaf in a free tree. This is another leaf in a free tree, for example. If this were a free tree. And pretend this didn't have a root. here would be a leaf, here would be a leaf, here would be a leaf, here would be a leaf. It's just anything that has one edge coming out of it, any node. And yeah, that was subtree. I think that's all the terminology stuff. We talked a lot about traversals of trees, pre-order, post-order, all that fun stuff. Remember what terms all meant. Pre and post, we're all talking about in what order do you visit the root before you talk about your children. Pre means root first. Root, then recursively visit your children, then children. Post is children first, then at the end becomes, we look at our root. So children first, then root. All right, let me draw that better. And then in order is left root right. It only works for binary trees because there is a concept of left root right. And of course, when I say left and right, I mean recursively in order, left and right. All right, so let's do all that. And then breadth first search is level order from left to right. So here's an example tree where the root's up top. And let's make this be our tree. So here is, looks like this. Let's give our nodes names. This can be A, B, C, D, and E. So pre-order, I'll use a different color for all these. So pre-order is gonna visit, you always start the traversals from the root. It's gonna visit the root, and then it's gonna recursively visit the two subtrees. And so A is definitely gonna be output first, and then it's gonna go recurse left, pre-order the left subtree, which is again going to go root, and then pre-order the children. So it's going to see B, then D, then E, because we're usually going to go from left to right. So it's B, then D, then E, and so then the left pre-order is done. We do the right subtrees pre-order, and that's everybody. So then we see a C. So that's the pre-order traversal. Post-order would look like this. It's always children, then root, in order though. So we're going to recurse left, post-order right subtree, then talk about the root. So the A is going to appear last now. So it's post-order this, which means post-order children, then visit the root. So it's going to be DEB. And then we did this one. Then we post-ordered the right. It's just C. And then we post-ordered both the children. And now we can visit the root. So then the A appears. So that's the post-order order. Then we have the in-order order, which is always left root then right. That's the other possibility when you have a binary tree. So it's recursively in order the left subtree, which is again going to be like recursively in order this subtree now. So it's left root right. So it's DBE that we see when we go down there. DBE. Then we did this one, then we do the root, then we do the right. So A and C. You'll get fast at it like me if you're not there already. Just do practice. And then breadth first is the easiest. It's just level order. Boop, 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 in that order. So it's legitimately, given the way that I numbered things or labeled things, it's A, B, C, D, E. Okay? So those are your traversals, and that's the order that you get stuff out in. That's the order that you visit things in. You can also traverse graphs. The common ones were breadth first search and depth first search. They create trees. They create trees in which you discovered things, which edges you followed and stuff like that, which is interesting in itself. But here is, let me make a graph for us, and we can talk about traversals of that graph. So here's an example graph. Let's say we have these edges, and then it looked like this. And this is A, B, C. Let's say this is A, B, C. I don't know, it could be anywhere. D and E, apparently, is what I did last time. So there's a graph, and let's do depth first search on it, or depth first search traversal, and breadth first search traversal on it. So I'll have two copies of the same graph. One for breadth first and one for depth first. Let's do DFS first, because that's the first one here. It's essentially the equivalent of post order for graphs. It's like go as deep as you can into your adjacent edges, then deal with yourself. Then root, after all that's over with. So here's depth first search. Let's pretend that we're doing depth first search starting from A. So you're going to go down every edge. It's like visit all your children as long as there's stuff that you haven't seen yet. So it's like, all right, A is the first thing that we visit, of course. Then we start following edges. Let's break ties by doing the smaller one in order. So B versus E. B is smaller. Let's go down B's edge. So that's going to be part of this green edge is now going to be part of our depth first tree that we're creating as we're visiting everything. And so then we're at B, and then we visit from B. It's like follow any edges that are not yet to nodes that we've not yet seen. So B is the second thing we see, and that leads us to E. And that will be the third thing that we see. And again, follow any edges that lead you to things you haven't seen yet. So we're going to D. That's the fourth thing that we see, and then we're going to C. That's the fifth thing that we see. And then the recursion unwinds. It's like, is there anything else? And then visit everything from C that's unvisited. There's nothing. Then we come back, pop ourselves off the recursion stack. Now we're back looking at D. Is there anything else left to see? No. Then we're back at E. Is there anything else left to see? Well, we could follow this edge, but we've already seen A, so we don't. And then we're back at B. Is there any other edges to follow? No. Then we're back at A. Are there any other edges to follow? Well, originally it wanted to follow this one, but we got to E already anyway. So that's going to be our depth first traversal. That's supposed to be a green edge. And this is the order in which it visited and saw those nodes. First, it tries to get as deep as possible into the graph. That's depth first search. Breadth first search likes to stay up close to the starting point as long as possible, just like this guy. Like A, then B, C, then D. And so it'll use a Q to do all that, but I'll just draw it. Again, let's pretend that we're starting our breadth first search from A. What it's going to do is it's like, all right, I visited A first, and then push B, these edges, like follow these edges, push those to like a Q. So it pushes the fact that it found B, it pushes B to the Q, and then it also follows this edge to E, because E is also unvisited, and it pushes that to the Q as well. And now B is like at the front of the queue. It's like that's the second thing that I visit. I'm going to push all the edges to things that I haven't seen yet, but we've seen B and E, so we're good. And now E's on the top of the queue. Try drawing the queue, I think it would help. And then it's like, all right, let's go to all the places that we haven't been yet from E. And it's like, all right, apparently there is, let's see here. There's D left. Can't follow to B because we've seen B already. And so we have D, 4, and C from there. That's like, then we push D to the queue and we follow all of its things. It eventually works out. And so surprisingly, this leads to a similar yet different tree. Mostly the same though. So it's like, stay as close to A as you can. Like these two next things that we see are 1 away from A, and so that's why it draws it like that. And then this was like 2 away from A, and this was like 3 away from A. That's why it's drawing it like that, rather than like going as deep as possible as a snake. It likes to stay close to the top. That's breadth first search. And so those are your traversals. See if you can get those down in your mind, and yell at me if you have any questions about anything. But I believe that's where I want to stop. That's a good halfway point in the review slides. So I will see you next week for the next half.